Welcome to this presentation of the Rotary Club of North Bethesda, Maryland, USA. Our club was established in 1974. We meet every Friday morning at 7:45 a.m., and we often invite guest speakers to give presentations on all kinds of interesting subjects. Please contact us through our website at nbrotary.org. And thanks for watching.
To turn the floor over to Linda, who's going to introduce our esteemed speaker. Linda.
Okay, I'm very happy that Stephen Leete has agreed to come and meet with us today. He has worked at NASA for many years and was involved in 3 Hubble missions. He is currently, hold on, this is Stephen, very hard to introduce because truly I understand nothing of what you do. So let me quickly say you are a staff engineer lead systems engineer for mission robotic vehicles at Northrop Grumman. And I'm sure he's going to stick around and be available for questions. This is somebody who's had 35 years of experience and certainly will let us know a lot more about Hubble than we ever do. And Hubble is one of my favorite things to try to understand. So,
all right. Well, thank you very much. All right. So welcome everybody. I'm Steve Leete, and I'm going to try to share my screen and share my sound, which I actually don't entirely remember how to do. I have muted the microphone on my computer, but I am going to want to share.
And then you do from start.
All right. Very good. All right. So yes, I retired from NASA, but that's a financial thing. I still work very full time. In fact, the last few weeks have been crazy. All right, so you may not be able to see a few things. Whoever's controlling the screen up there,
you're controlling that.
And maybe if you can minimize the people on the side.
There you go.
Well,
We can see everything on the screen,
I just
Steve.
lost it.
all right, I'll.
Oh, there you go.
Okay, so yeah, I had a brief bio here, but I won't spend much time on that. But I did work on some really interesting missions while at Goddard, NASA Goddard for 30 years. Cosmic background explorer, we confirmed that the Big Bang Theory was the correct story of the origins of the universe, and 2 of our physicists won the Nobel Prize in Physics for the work on that, including the particular instrument I worked on. Worked on a Cassini instrument that worked right up until the day that the Cassini had to dive into the atmosphere at the end of life about 4 years ago. Anyway, and then I worked on 3 Hubble service missions out there, and now I extend the satellite servicing into the commercial sphere with mission robotic vehicle, where we go after the geostationary Earth satellite belt and service satellites there to repair them, extend their life. So fun stuff. All right. So Hubble Space Telescope. It's nicknamed the People's Telescope.
You can't hear the speaker.
Because NASA had at one time canceled the last servicing mission, and the people of the United States, taxpayers, said, "No way, are you going to do that?" And Congress had to intervene and say, "No, we're going to give you the money, spend the money, keep servicing Hubble. We love Hubble." Right? So it's one of what NASA at the time was calling the Great Observatory. So back in the 80s, we had this plan where we were going to put up these very large observatories that would that look out into the universe in different portions of the electromagnetic spectrum. right? So there's the visible light that we can see with our eyes, and then on the edges of that, there's infrared and ultraviolet. But then there's also gamma rays. So we have the quantum gamma rays observatory, deeper infrared with the Spitzer Space Telescope, and then X-rays, Chandra. So Hubble was one of 4 great observatories at the time. Originally thought of at the very beginning of the space program, when we were first starting to think about being able to put something into orbit. The scientists said, oh, it'd be great if we could put a big optical telescope out there. You can see things, there's frequencies of light that where the atmosphere is opaque, we literally can't see through it. And, we'd be able to do all these great observations. If we could just get a nice big telescope out into space, let's do it. And a few decades later, it happened. Let's see what else. And Hubble was done as a joint mission with the European Space Agency. So we were not in on this all by ourselves. It was built largely at the NASA Marshall Space Flight Center in Huntsville, Alabama. And Lockheed Martin, or just Lockheed at the time, Sunnyvale, was actually the factory where it was assembled. And it was launched in a space shuttle in 1990. Now, it was, let's see, right. So the telescope, the primary mirror is 10 feet in diameter. So, 2.4 meter diameter, 10 feet. And it was very difficult to make. And there's some wonderful history. Whenever we've made breakthroughs in making really large primary mirrors for new telescopes, like the Palomar telescope, it's always opened up huge new areas to explore. And Hubble was very much like that. The company that made it was very proud of their accomplishment at making this huge mirror that could go through the rigors of being launched into space with all the shaking and everything, and stay in perfect alignment, and not, and the glass mirror not break. It was really a tremendous accomplishment. Now, Hubble was always intended to be serviced in space by astronauts. That was the original concept of it. Now there were some challenges there because you had to spend extra money to make it serviceable. Right? You had to put handles on the outside. You had to put doors on the outside so that astronauts could go up there and open doors and get to the things that are on the inside. And as it was costing a lot of money to produce it, people wanted to cut the budget and save money. It's like, oh, we're going over budget. And so they cut back on all that stuff, and people put it back in, and thank goodness, because what we ended up with was something that astronauts could maintain and improve over time. And so I give credit to some of the people, Ron Sheffield in particular, was a great guy who made sure that all of those aspects were in place. And it was launched in 1990. Okay, so are people having trouble hearing me? No. Maybe. All right. So this is what Hubble looked like in April of 1990. In a picture taken from the payload, or from the where the crew was inside the space shuttle. So that is the Canadian arm that was part of the shuttle. Letting go of an attach point and letting Hubble fly free after it had deployed these big solar arrays. So I have a model of Hubble, which I guess people can, well, I don't know, maybe. So for the people in the room, this is a working model that so every time we serviced it and Hubble was changed, like we added things on, we would get a new copy of this model so that it was up to date. And we would sit in meetings and conference rooms. And so instead of saying, oh, well, we're going to go into this door and try to remember where it is, we would say, okay, we're gonna have the astronauts climb up on these handrails, and they're gonna move over to this door, and they're gonna open these 4 bolts, and and so we could know exactly what we were talking about. All right. So, so this is what's on the inside of the Hubble Space Telescope, right? So light comes in at one end, bounces off the big primary mirror, goes up to a secondary mirror, and then a focused beam of light comes down to 8 different things, 5 science instruments, and 3 instruments that are called, actually I don't have it on here, but fine guidance sensors, which help point the telescope very, very precisely at a particular point in the sky.
Where are the glasses?
I will get to that. So anyway, all of this, and so these science instruments are held in by latches, and an astronaut can come up there, open a couple of doors, turn a couple of bolts, and slide one of these phone booth-sized instruments out. So these instruments are about 6 feet tall and 3 feet wide and 3 feet deep, and they weigh about 1,000 pounds, and the astronauts can just pull them out with fingertip control because they're weightless. You know, they're massive, but they're weightless in space. Really. So and here's kind of a blow up diagram of what things look like on the inside, but I won't. So how big is it? So it's about the size of a school bus. It weighed 24,000 pounds. That's 12 tons. So it's 14 feet in diameter on the outside. The mirror is 10 feet in diameter. So it's not as big as the rest of it. And it was launched into a 340-mile-high orbit, which is as high as the space shuttle could possibly get. Most of the time, the space shuttle did not fly that high. So that's 547 kilometers. The space station, for instance, is at 400 kilometers. So the idea was the Hubble doesn't have any rockets on it. Most satellites have rockets on them that allow them to fire thrusters and stay in whatever orbit you put them into initially. Hubble is not like that. And the idea was that you didn't want these gases getting onto the mirrors and degrading the optics. So the shuttle would come up, grab hold of Hubble, and while it was also doing all this servicing, the shuttle's rockets would fire and they would raise the orbit back up to as high as that shuttle could get it and still get the astronauts back home safely. And so it would be periodically reboosted every time it was a servicing mission, and then it would slowly come back down towards Earth over time.
How's it done?
So it has reaction wheels, okay, and so it's, I don't know, it's so hard to describe how satellites work, but so a reaction wheel, an individual star looked like that weird pattern on the left there. So the light that is supposed to be in a very tight little spot was spread out all over the place. And so every individual point of light that they looked at with the telescope looked like this. All right. And some scientists were able to look at that pattern and say, wait a minute, that looks familiar. That looks like a certain particular kind of optical problem that I've seen before. It's called spherical aberration. The words are down here. And so what it did is it took the light and it spread it out so that only about 1% of the light was in the middle and the rest of it was spread out all over the place. and by playing around with some equations of spiritual aberration, all like that, they were able to apply the inverse of that problem to the light that came down and turn it back into a small point of light again. But by throwing away 99% of the light. And so they were able to
Somehow lost presentation up there.
yeah. There we go. All right. Well, when the news came out, NASA was a laughing stock. They adopted Mr. Magoo as the spokesperson for the Hubble Space Telescope. Anyway, it was terrible. NASA's $1.5 billion blunder, and that was real money back then. So there was a lot of back and forth within the team, but ultimately it was figured out exactly what was wrong and exactly how to fix it. And so the answer was to remove one of those 4 telephone booth-sized instruments and replace it with something that had the same size and shape and latches and everything, but just had corrective optics in it that could be pushed out on a boom and deploy mirrors out in front of the other instruments and take in light from the mirrors, change it, and then inject that light into the other instruments. And then the other instruments would work perfectly well. And there was a 5th instrument which got its own corrections just for itself. That was a bigger instrument that took nice big picture live film camera. So we removed 2 instruments, put in replacement instruments that had the optics corrected, and that fixed the optical problems with the Hubble Space Telescope. We didn't touch the primary mirror or the secondary. We didn't touch the telescope, the 2 element mirrors of the telescope itself, but we corrected the beam afterwards. So it's like you've got glasses that are the wrong prescription, so you put another pair of glasses behind your glasses that aren't working right. So this is one of the instruments that was taken out. Looked like this. So this is so astronauts train underwater. So if it looks like in this picture here, it looks like they're underwater. You can actually see there's a scuba diver behind here, right? So the cool thing about the best way that we have found to train astronauts for being in zero gravity is to put them underwater, which is kind of counterintuitive, but it works. It works great. And you can also make big, heavy objects like this appear to be weightless by putting styrofoam on the inside. And you put the styrofoam in just the right place so that they're not only neutrally buoyant, but you can turn them any angle, and they don't tend to right themselves. They don't have a preferred orientation either. And I was one of the people that would help make that happen, right? So we had a crew of people that would build these mock-ups, make everything appear weightless, prepare it for the astronauts, and then help the astronauts train. And so here's what it looked like in the pool, and then here on the bottom left here is the real deal, where an astronaut is handling that same astronaut, thing that actually, has a mass of 1,000 pounds or so, but it behaves just like it did underwater because it's weighted. So, image on the left is what a galaxy looked like with the bad optical problem, and this is what it looked like after they replaced the instrument that had taken the bad picture with a better version of that instrument that would take really sharp images.
Excuse me, is that a sun star in the middle of that?
So in the middle is the center of a galaxy. This whole picture is a galaxy.
Okay.
Right? So we've taken fabulous images of Jupiter and all sorts of stuff. And there's some really exciting stories of things that happened during the service of missions. This I love. We have an instrument that can combine infrared, visible, and ultraviolet. And the people that process the images have figured out how to combine, this wide range down into our, compress it down into the visible range, and just produce these spectacular images. Now here we see what happens when you see the visible dust that obscures our vision. But if you look at it with infrared, that stuff fades away, and you can see all the stars that are hidden behind the clouds. And we've taken, I don't think I have it, but we've taken many pictures over time of this and made movies of them. And so you can see what has happened over decades in kind of a time-lapse sort of way.
Is that a supernova?
That is, it is a nova. It is a star that exploded. Yeah, and spewed contents out all over the place. All right, I'm going to cut to the end. Oh, wait a minute. I do want to show this. So this is the Hubble Ultradeep field, where we look at a point in the sky where there are no stars from our galaxy. So right, our galaxy is kind of a plane, and so if you look perpendicular to the plane, instead of seeing the stars in our galaxy, you can see just stuff that's outside of our galaxy. So that's what this is. And every point of light in this image is a galaxy. And the little bitty ones are galaxies that are on the order of 10 billion light years away from us.
It's just boggles the mind.
Oh, and this is gravitational lensing. So when you have a cluster of galaxies near us and they distort the light coming from galaxies that are farther away, Einstein predicted that it would smear the light out into arcs. And here are images like that, where it's a cluster of galaxies, and then these are distorted images that are quite distant galaxies. Okay, so I want to just play something for you. So I'm also a singer and an actor, and I had a lot of fun out there. But I started up an Aquapolis singing group while I was at NASA. That group had a couple of PhD astrophysicists that started writing really great songs, and I would like to play for you my favorite of those.
It was a calm and cloudless night, but it was all still a blur.
Good morning.
The shaking of our universe was just about to occur. It was summertime, 1609, when Galileo used his telescope for the very first time, and he saw mountains and craters on the moon,
So I am here to talk
and
about
a
the
Milky
space
Way with
superhighway.
thousands of
Thank you,
stars.
Steve, for
Then
handling
he
the
saw
information side
Jupiter
of this
with 4
This is
tiny
really
moons.
the
He
hybrid.
was the only man on Earth that night who
This is the hybrid
knew
moving stuff.
that Copernicus was right. Come outside with me tonight, and I can show you wonders of the world to surprise and delight. I've got my telescope with me. Just wait until you see that on the shoulders of giants
One other
we'll see
back reference to Steve's talk.
beyond.
This doesn't have the majority. I don't have a 20-person version. Endorsed 40-star.
The world turns round and round, and now around 400 years have flown since Galileo.
So the development of digital photography, I'm not a complete expert on the exact timeline of who developed what first and what, but someone asked, are these digital images, right? And so the Hubble developed these really amazing electronic sensors for collecting images and turning them into digital and creating digital images, and we really push the state of the art of focal plane detectors for taking imagery. And we have shown that that led directly to much better breast scan images, and really the whole digital photography field was sped up quite a bit by the development of instruments for Hubble Space Telescope. We're going to throw this together quickly, and we'll have other big telescopes that we will make serviceable later on. And then that turned into a like $9 billion, 15-year development program. So there's nothing quick about it whatsoever. Yeah. So we were kind of sold the bill of goods.
The other
be patient.
I don't know. I could get to high orbit, and then tweaking it, testing everything out before they put it into the L2
Yeah, so the rocketry works out that you want to just shoot it straight out there. Okay, it's the orbital mechanics are not very good for doing something halfway in between. But the orbital mechanics of sending things out to Sun Earth L2 are really interesting. And I actually instigated our orbital mechanics people at Goddard to collaborate with me on a paper of how we could bring James Webb back not to, well, to Earth orbit near the moon and work on it there, and then take it back out to the Sun Earth Lagrange point again.
Right.
The trick with something that's that big with kind of delicate things is you can move it around with rockets as long as they're not very strong, and so as long as you don't try to do anything too violent to it. And it turns out that to get from 1 million miles away to a 250,000 miles away, which is where the moon is, it doesn't take much, and you can just kind of gently nudge it and bring it back here, and then you can gently nudge it again to send it back out. And that would work, and that may happen someday.